In this video, we're going to look at what's called implicit differentiation. And we're going to start off with a definition just to understand the context of what we're doing here. So here's our definition. Let's put that in a box. We're going to say that y is an explicit function of x if we have a function where we have actually solved for y. So an example would be the situation here. We've got y on the left side, no y's on the right side. So something like y equal x minus 1 over x plus 1 would be an explicit function of x. Similarly, any sort of polynomial where we've got something like, say, y equal x cubed plus 2, for example, that would be a situation where y is an explicit function of x. So the other situation, let's look down here, would be where a function y is an implicit function of x. So that's a situation where x and y are related in some equation, but we do not have y on the left side of the equation. So if we looked at something like x squared plus y squared equal 1, okay, we've got an equation where the x and y are all tangled up. The y is not sitting on the left side of the equation. So we say that y is an implicit function of x in that situation. And we could have more complicated equations that might even have more than one instance of y in it. So something like 5x minus 3x squared y equals 4 over y. Okay, x and y are related by an equation, so that means that y is a function of x. But because we do not have y solved for on the left side, it's not an explicit function of x. So we actually call it an implicit function of x in that situation. So if someone gives you an equation, like this bottom one, for example, it can be difficult or sometimes impossible to solve for y. So what we're going to be working towards in this video is how to take the derivative of y with respect to x when we're in this kind of situation here. So we'll do a short example, and then once we've done a little bit of warm-up, the actual process will become clear. So let's look at this short example here. Okay, we're going to do two parts, and in each part, y is an implicit function of x. So that just means that you could say y depends on x, or you could say y and x are related in some way. We don't know the exact equation that relate x and y together, but we're just going to store it away in the back of our minds. Okay, somehow x and y are related. You know, maybe we've got something like x cubed plus y cubed equals 12 or something like that. What we want to practice here in this short example is just how to take derivatives. So part A, if we want to find the derivative with respect to x of a function that involves x, this is just our normal derivative process. So we'd say derivative with respect to x of 4x squared is 8x. We learned that back when we saw derivatives of polynomials. But things change if instead of an x, we've actually got a y in this function. So in part B, we're looking at the derivative with respect to x of 4y squared. Well, now all of a sudden there's a chain rule involved, because our outside function is this function that takes a quantity, like y. What it does, it squares it, and then it multiplies it by 4. So our outside function takes blah, it squares it, multiplies by 4. The inside function is actually the y. So according to the chain rule, we know that we're supposed to take the derivative of the outside function first. So that would look like 8y. And then we should multiply by the derivative of the inside function. Well, if y is the inside function, then that derivative would look like dy by dx. So according to the chain rule, we get 8y times dy by dx. So the way to tell the difference between these two situations is you can just say to yourself, well, anytime in this section where we're given y is an implicit function of x, so that's the context here. Anytime x and y are related by an equation. When you're taking derivatives, let's just think of it as we need to multiply by dy by dx when we're differentiating a y term. So in part A, taking the derivative of an x term, you could say that just works like normal. You get 8x. But in part B, we took the derivative of a y term. So we wrote down you could say the obvious derivative, which is really the derivative of the outside function, 8y, and we say, oh, but because that was a y term that we differentiated, we need to then multiply that by dy by dx. And the reason is the chain rule. So let's try a couple more parts. We'll break into a new page and just practice this concept. Let's continue our previous example. We're just going to practice a couple of taking derivatives. So let's say we want d by dx of x cubed minus 2y squared plus y. I think that would be a good one to practice. Okay, so we're just going to read across from left to right here, take our derivatives. So derivative with respect to x of x cubed is 3x squared. Derivative with respect to x of minus 2y squared is going to be minus 4y times dy by dx. Remember, anytime you're differentiating a y term, you need to multiply by dy by dx due to the chain rule. And then last term here, derivative with respect to x of y. Well, you could just sort of think of this notationally, and you could say that would be dy by dx. Or you could think about it according to our rules. You'd say, well, derivative of the outside function is 1. So you'd take that 1, and then because that was a y term, multiply by dy by dx. So two ways of thinking about that. Either way, that last term just becomes plus dy by dx. Okay, so let's try one more like that. Part D. Let's take d by dx of 9xy. Okay, so this kind of situation where you have an x term and a y term multiplied together can tend to be a little tricky. So what I like to do before I even take the derivative, usually like to do just a little rewrite here. Let's take this 9xy and let's specifically break it up as something involving x times something involving y. And the reason I want to be clear about breaking it up is because we are going to use the product rule here. Okay, so let's remind ourselves of our product rule over on the side. Product rule says if you want to take the derivative of uv, you go uv prime plus vu prime. So it's just really helpful when there's a lot going on in a problem to be clear about what your u is and what your v is before going into the calculation. Okay, so we know that u is 9 times x. We know that v is y. And again, we broke it up so that all the x terms would be in one factor and any y terms would be in the other factor. It just makes things go a little bit more smoothly with the differentiation. Okay, so now let's apply our product rule. So first factor, 9x, times the derivative of the second factor. Well, derivative of y with respect to x is just what we call dy dx, dy by dx. Okay, and then we go plus and do it the other way around. Y times the derivative of 9x with respect to x. Okay, so that would just be 9. And then if you wanted to clean this up at the end, you could say, oh, okay, well, y times 9, we'd probably just write that as 9y. So notice that in the first term here, you have this dy by dx. That's because we were differentiating a y term. And then notice that when you did your second term of the product rule, we were taking the derivative of the first factor. When you're differentiating an x term, everything just goes as usual. So we did not have the dy by dx coming up in the second term. So here's our main idea of what we're going to be doing in this section. So the main idea of what's called implicit differentiation is that we can actually find dy by dx without solving for y first. Seems kind of amazing and maybe even counterintuitive. So you might have, a fairly messy equation, like in a moment we'll jump into this example here. You might have some equation like this where x and y are related together. It might be difficult or impossible to solve for y, and yet there's a fairly quick process for finding the derivative anyway. So that's what we're going to be looking at here. The process is called implicit differentiation. And the only thing it really relies on is just this sort of warm-up problem that we just did, these 4 parts, where we keep in mind that whenever we're differentiating a y term, we're going to need to multiply by dy by dx. So let's jump into our first big example and we'll see how implicit differentiation works. Okay, so here's the problem. We're going to find dy by dx. We're going to do that at a specific point. for a given implicit function. Okay, so when you have an implicit function of x and y, meaning you've just got some equation in which x and y are tangled up, it's typically hard to graph, but often you'll have some kind of curve that doesn't necessarily pass the vertical line test. So it could be something kind of loopy like this, for example. So let's say that we've got this point, 0, 2, which lies on the graph of that curve. So the problem is to find the slope of the tangent line at that point. Okay, so that's what we're going to do here. So these implicit differentiation problems, they have two parts. Let's break into a fresh page and we'll just go through all the details here. So here we've rewritten our problem. We're going to find dy by dx at a certain point for this implicit function here, 5x minus 3x squared y plus y squared equal 4. So first main step is we're going to take the derivative with respect to x of both sides of this equation. So we're just starting with this implicit function here, just go through term by term and take our derivatives. Now, if you see in any of the terms, if you see a product where you're multiplying something involving x times something involving y, you may want to just do a little bit of extra writing before you jump into your calculation. So for example, for this term here, you might want to think of that as plus, let's call it minus 3x squared times y. Okay, and the reason I want to do that is because there's going to be a product rule involved when we take this derivative. And if we have it explicitly written as a product so that it's really clear what our factors are, it just takes off a bit of mental pressure, when we're trying to apply the product rule. Also, if there is a negative, you can consider bringing the negative into the brackets, just like we did here, and then just making the whole term plus. Just also makes things slightly easier. Okay, so let's jump into the taking of our derivatives. So anytime you see an x term like 5x, the derivative works as normal. You'd say, okay, derivative is 5. Then we get into this product. So we're going to do product rule. I think I'll put that in brackets just so we can see that happening. So first factor minus 3x squared. That gets multiplied by the derivative of the second factor, dy by dx. And then we go plus, we do it the other way around. So y times, and then we're going to take the derivative of the minus 3x squared. So minus 6x. So anytime you differentiate a y term, you get this dy by dx multiplied on there. Anytime you're differentiating x term, things work as normal. Okay, and then finally, taking the derivative of y squared, you'd have 2y times dy by dx. Over on the right side, derivative of any constant is 0. Okay, so that's sort of the hard part of the problem, is taking derivatives of both sides of the equation with respect to x, and just remembering that if it is a y term that's being differentiated, we have to multiply by dy by dx. Okay, second major step is now we're just going to solve this equation that we've just created for dy by dx. So what that means is we want to get all the terms that have dy by dx in them on the left side, and we want to get all the non-dy by dx terms on the right side. Okay, so let's start to clean this up. So these square brackets here in the previous step, they were not strictly necessary because we're just adding a bunch of terms together. I just really put them on there so that you could see which terms belong to the product rule. So we can do that. Okay, so I see a couple of terms that have dy by dx in them. So those are going to stay on the left. We're going to have minus 3x squared dy by dx. We're going to have plus 2y dy by dx. The other two terms are going to move over to the right and they'll change their signs. So we'll have a minus 5, and then we'll have, we can call this guy here a plus 6xy. So now that you've got only dy by dx terms on the left, you can factor. So pull out a dy by dx. We're left with minus 3x squared plus 2y. Stuff on the right stays the same. And then magically, we can divide by all the stuff in the brackets here, and we will have our dy by dx. So it's minus 5 plus 6xy over negative 3x squared plus 2y. Now in this problem, we were actually asked to evaluate at a certain point. We can scroll back and just see that question there. Yet we're asked to find the derivative at the point where x is 0 and y is 2. So let's sub in, we'll actually have a numerical answer here. So we'll write dy by dx evaluated at 0, 2. Okay, so plugging in x equals 0 and y equal 2, we have negative 5 on top and we have 4 on the bottom. So that's the answer, negative 5 over 4. Let's just look back to the original problem where we had drawn an intuitive picture. So I'm looking at this picture here. So we said often implicit functions are something that have sort of loops in them or something like that. What we did is we found the slope of the tangent line at the point where x equals 0, y equal 2. So we are going to find dy by dx given 4x cubed y plus the fourth power of y cubed plus x is equal to 16. Okay, so first step, step 1, let's take d by dx of both sides. And if you see any terms in your equation where you're multiplying something involving x times something involving y, as we do in the first term here, you may wish to put brackets around that, just because that will help us figure out the product rule when we get to that point. So the first term has a product between something involving x, something involving y. The second term does not have that form. See, the y and the x terms are just added together. That's okay. All right, so let's take d by dx of both sides. So first term, we're going to do our product rule. If we want, we can write the product rule out again. uv, all primed, is uv prime plus v u prime. Okay, so we'll take our first factor, which is 4x cubed, multiply by the derivative of y with respect to x, so that's dy by dx, plus, we're going to do it the other way around, y times the derivative of the first factor, which is 12x squared. So that's our product rule done. Then we get into the second term here. So we're now looking at this guy. So let's take the derivative of that using the chain rule. And I'm just going to make a little bit more room here. Okay, so taking the derivative of the outside function, the 4 would come down in front. The power would decrease to 3. We'd keep the inside function the same. Okay, and then we need to multiply by the derivative of the inside function. So think of this stuff here as being our g, our inside function. Remember when we were talking chain rule, we always called that inside function g. So we need to multiply by the derivative of this thing. Okay, so we'd say, well, the derivative of y cubed is 3y squared times dy by dx, because we just differentiated a y term, plus the derivative of x with respect to x is 1. Okay, so that's our chain rule in action. And then continuing to take derivatives of this equation here, we say that equals 0 because the derivative of any constant is going to be equal to 0. So that's our differentiation done. But now what we need to do is solve for dy by dx. And, you know, that may take 4 steps or so, depending on the problem. So we'll just be patient here and we'll start to gradually clean this up. So first thing I'm going to do is just try to make these terms look a little bit better. We've got 4x cubed dy by dx plus our second term, let's call that 12x squared y, plus, okay, now we've got basically this whole thing, which we would like to multiply with the stuff in the brackets, because the idea is that we're going to need to separate the dy by dx terms from the non-dy by dx terms. So if you see a bracket like this where you've got a dy by dx term added to another term that does not have dy by dx, you'd have to actually expand this out in order to separate those guys from one another. Okay, so let's do this first multiplication here. Well, the 4 would multiply with the 3y squared to give us 12y squared. We'd have the whole cube on there as well, y cubed plus x. and then we'd have a dy by dx on there. So the thing is, when you're multiplying something like this, just make sure that dy by dx goes at the back. That's just the conventional way of writing it, and it will help when we're factoring it. Okay, and then doing the second multiplication here, we just get 4 times that cube, the cube of y cubed plus x, and all of that is equal to 0. So with this term here, yeah, there were a lot of things to multiply, so we could just now go back and check that we've accounted for everything. So we took the 4 times the 3y squared to give us 12y squared. We've got the cube on there, and we've got the dy by dx on there. So I would say it's okay to double check that after you've written everything down. Now that we've done that, our goal is to get the dy by dx terms on the left and everything else on the right. So we've got 4x cubed dy by dx, plus we've got this 12y squared times the cube of y cubed plus x times dy by dx, and other stuff is going over to the right with sign changes. So minus 12x squared y and minus 4 times the cube of y cubed plus x. So now we're going to do a little bit of factoring. On the left side, pull out that dy by dx. We'd have 4x cubed plus 12y squared times the cube of y cubed plus x. Right side will stay the same for this step. And then, once we've got that done, just one more step to go. We just need to do our division. So dy by dx equals this whole right side divided by the stuff in the brackets from the left side. So the 4x cubed plus 12y squared times the cube of y cubed plus x. So that's our second example of implicit differentiation done. So third big example here, we're going to find dy by dx given x plus root x times y equals root y. One thing we might want to do, because we know there are going to be derivatives coming up, you may prefer to write the root x as x to the 1/2 and the root y as y to the 1/2. That's up to you, whether you think that's going to make your life easier. And then if we've done that optional step, first thing we're going to do is take the derivative with respect to x of both sides. If you see any products that involve something in terms of x and something in terms of y, you may wish to put brackets around that just to make your life easier when you do the product rule. And if you want, you can just sort of scribble the product rule over on the side. So derivative of u times v, u v prime plus v u prime. So all of that might make your life easier as we go through the calculation. Okay, so taking derivatives with respect to x of this equation here, we'd have 1 plus, we're going to do our product rule, x to the 1/2 times dy by dx, plus, now do your product rule the other way, so y times, we need the derivative of x to the 1/2, so that'll be 1/2 x to the minus 1/2. So that's our product rule. And then that equals, well, now we're going to do the derivative of y to the 1/2. So that's 1/2 y to the minus 1/2. And because we just differentiated a y term, we multiply by dy by dx. Great. So we're going to keep the dy by dx terms on the left. So let's start to write those down. X to the 1/2 times dy by dx. Let's make that a little bit easier to read. So x to the 1/2 times dy by dx. We've got a minus 1/2 y to the minus 1/2 dy by dx. And then the two other terms are going to go over to the right side. So we'll have a minus 1 and we'll have a minus 1/2 x to the minus 1/2 times y. Great, so we can do some factoring here. Pull out a dy by dx and you'd have x to the 1/2 minus 1/2 y to the minus 1/2 equals this right side. So nothing's changing on the right side at this point. And then final step would be to just divide through by whatever's in the brackets so that we can isolate that dy by dx. So we'll have -1 minus 1/2 x to the minus 1/2 times y all over x to the 1/2 minus 1/2 y to the minus 1/2. Now, if this question specifically asks you to simplify, we're going to just do a little bit of algebra practice while we're at this. If we wanted to simplify this, what that would mean is to clear the fractions and also the negative exponents. So the things that make this not so nice to work with, if we were doing a follow-up question, it's not so nice to have a fraction then divided by something else, and it's also not that convenient to have a negative exponent when you're then dividing by something else. So the way we're going to simplify, if we're asked to simplify, we can multiply top and bottom by anything we like, but if we wanted to get rid of the half that's sitting on top and on the bottom, we could multiply by 2 over 2. See, that would clear all those fractions. We could also multiply by x to the 1/2 on the top and the bottom, because as that multiplies through, that's going to multiply with this guy to give us x to the 0. So that'll get rid of the negative exponent on the x. And then similarly, you might notice there's a negative exponent on the y in the denominator. So if we go y to the 1/2 over y to the 1/2, that'll be good enough to clear all the negative exponents. So you would only have to do this part if you were actually asked to simplify your answer, but always good for us to practice the algebra whenever we have the opportunity. So I'm going to put brackets around this, and we're just going to expand out in our next step. Okay, so dy by dx, multiplying the top through by this 2x to the 1/2, y to the 1/2, we'd have minus 2x to the 1/2, y to the 1/2. In the second term, the half and the 2 cancel. The x to the minus 1/2 and the x to the plus 1/2 cancel. And you'd have y times y to the 1/2. So when you're multiplying, you're going to add those exponents together. 1 plus 1/2 is 3/2. Okay, so that's what we're getting on top. On the bottom, continuing to multiply through by 2 root x root y, we are getting 2 times, if you multiply a root x times a root x, you get a full x. And there's also a factor of y to the 1/2 on there. Okay, second term, the half and the 2 cancel. We'd get an x to the 1/2, and the y to the minus 1/2 cancels with the y to the plus 1/2. So that's all we're getting there. So that's good in terms of a simplified answer. The other thing you might see happening is when there's a whole bunch of negatives in your expression, as there are here, there are 3 negatives out of the 4 terms. The other thing you can do is you can think about multiplying by -1 over -1. So that's just going to change signs of every single term. And because we're doing the same thing to the top and the bottom, we're allowed to do that. So another way to say that would just be 2x to the 1/2, y to the 1/2, plus y to the 3/2. So now everything on top is positive. And then changing the signs in the denominator as well. So minus 2x, y to the 1/2 plus x to the 1/2. So the reason why I mention this simplifying is just when you're checking your answer, let's say you're looking in the course pack and checking the answer for your work, just be aware that, you know, if you got, let's say, this answer here, you know, on a test, I would say, yep, that's correct. But the course pack, see, might be saying this answer, or it might be saying that answer. And the thing is, they're all correct. They're all just different ways of expressing the same thing. So if you're able to just look at that fairly quickly and understand that, yeah, they really are the same thing, just written different ways, that will help you a lot as you go through and solve various calculus problems. So last problem for this video, we're going to find dy by dx given x equals x minus y over x plus y. So we would look at that equation and we would say, okay, that's an implicit function, or rather y is an implicit function of x because the x and y are all tangled up. So we know we're going to use this process of implicit differentiation. And the first step is to take derivatives, specifically take the derivative with respect to x of both sides. So on the left side, that'll be easy enough. On the right side, we're going to need the quotient rule. So maybe not a bad idea to just remind ourselves of our quotient rule. If you want the derivative of u over v, start with the denominator. So it's v u prime minus u v prime over v squared. Okay, and we'll need to mimic that as we go through the calculation. So let's do our derivatives. So on the left side, derivative of x with respect to x is 1. On the right side, we're going to do our quotient rule. So take our denominator, multiply by the derivative of the numerator. Well, derivative of x minus y is 1 minus dy by dx. When you differentiate the x term, you get 1. When you differentiate the y term, you get dy by dx. Okay, and then we're going to go minus doing the numerator times the derivative of the denominator. So 1 plus dy by dx for the derivative of the denominator. Okay, and that's all over denominator squared. So now, second major step of the problem is to actually solve for dy by dx. And the biggest obstacle to doing that right now is the fact that we've got this big division going on. So after you've done your differentiation, you're free to multiply both sides of the equation by whatever you want. So we're free at this point to multiply by x plus y all squared. That's going to clear those fractions, clear the fraction from the right side. So on the right side, we've got x plus y times 1 minus dy by dx, and then minus x minus y times 1 plus dy by dx. Okay, now our goal is to separate terms that have dy by dx in them from ones that don't. So if we think of this x plus y squared, there's no reason to expand that out. That's just all non-dy by dx terms, so we would just leave that exactly as is. But as we move into the right side here, so we've got a non-dy by dx term that needs to be separated from a dy by dx term. So what we're going to do is we're just going to FOIL this whole thing out. Okay, so FOILing out, we'd have x minus x times dy by dx, plus the inside would be y, and the last would be minus y dy by dx. Okay, and then really same deal for the last term on the right side. We are going to need to FOIL this out. But a little thing that sometimes happens with algebra, see, sometimes you run into these triple products. A triple product is where you got something times something times something. So pretty annoying to have this minus sign out here. And the way that you can make life easier for yourself is you could say, well, instead of calling this minus x minus y, we could actually call it plus negative x plus y. So in other words, just bring the negative into the brackets there. The reason that's valuable is now we just have a normal product, right? We just have to multiply this with that. So that's basically going to save us a whole extra step of work. Okay, so let's FOIL this out. So we'll have negative x minus x dy by dx. Inside terms y, and last terms y dy by dx. Okay, so that's the sort of painful algebra close to done. So now what we're going to do is we're going to try to bring our dy by dx terms over to the left side. Maybe let's just cross them off as we do that. So we'll have a plus x and a plus y times dy by dx, and we got a couple more coming. We've got another plus x, and then that'll be a minus y. So we could say that's, well, actually, I'll try not to do too much in one step. So we'll bring the plus x dy by dx and then the minus y dy by dx. Okay, so we've taken care of all those four terms, and remember, all the signs are changing as they move over to the left. Okay, and then on the right side, well, we've got, let's see, we've got a little bit of cancellation, don't we? So the x and the minus x cancel. Okay, and we've got a y plus a y, so let's call that 2y. And then we'll bring this square over. Okay, so we've got 2y minus the square of x plus y. Okay, that doesn't seem too bad. And yeah, just making sure that we've accounted for everything. So that looks good. All right, let's try to factor on the left side. Just pull the dy by dx out of everything. We'd have an x plus y plus x minus y. That's pretty nice. The y's will cancel, and x plus x gives us 2x. So we really just got 2x dy by dx. On the left side, just recopy our right side here, and we are one step away from being done. So final answer coming up, dy by dx equals 2y minus x plus y all squared, and then just divide by whatever you've got in the brackets on the left side, so 2x. So that is implicit differentiation. It is incredibly cool and useful that you can find dy by dx without having to solve the equation for y. Thanks for watching.